So we would like to dig a little deeper in the notion of completeness and understand how it works for real numbers. So basically and technically speaking, we have said that R is complete, which means that every Cauchy sequence converges and let's even recall what these terms mean. So a sequence AN is convergent with limit L if for every epsilon greater than 0, there exists n not in n, such that for n greater than n naught, we have that an minus L is less than epsilon. So this tells you that the terms of an come arbitrarily close to L. On the other hand, and of course, in this case, we write that limit as n tends to infinity of an is equal to L. Now, an is Cauchy if its terms come very close to each other. So if for any epsilon greater than 0, there exists n naught in n, such that an minus am is less than epsilon for n comma m greater than n naught. And it turns out that the notion of completeness implies that the two properties, the two attributes, are precisely the same. So a sequence converges if and only if it is Cauchy. And we might as well shed a little light on how this is established for real sequences. And we should mention here, we should start by mentioning that the key is one of the fundamental properties of real numbers. In most presentations, it's taken as an axiom known as the completeness axiom. That says that every non-empty bounded above set of real numbers has a least upper bound. So if we were to draw a picture, we would take a real line and draw a set of numbers on the real line. And pretty much if this set of numbers happens to have a maximum, then that maximum is actually the least upper bound. So it's an upper bound for everything on that set. We should give some definitions here. So if A is less than or equal, is a subset of R, then S in R is called an upper bound. For A. If X is less than or equal to S, so no element of A exceeds S for every X in A. If A has an upper bound, then it's called bounded above. Please notice that we could define the same things on the other side, meaning we could have bounded below sets and lower bounds. But at least what we need to emphasize is that the least upper bound is a substitute for the maximum in case the set doesn't have a maximum. So as a simple example, if you take the interval 0, 1, the open interval 0, 1, then it doesn't have a maximum, but the number 1 is its least upper bound. And there is a very nice little characterization for the least upper bound. So S is the least upper bound of A. We also call it the supremum of A. So this is called the supremum. If two things happen, first thing, X is less than or equal to S for every X in A. And second, for any epsilon greater than 0, there exists X in A with X greater than S minus epsilon. This has a very simple and elegant meaning. The meaning is that we say that S is the least upper bound if whenever you try to push it by the smallest bit to the left, it stops being an upper bound. So you can find an element of X that is larger than S minus epsilon. So any attempt to replace S by a slightly smaller upper bound fails. Nothing less than S can ever be an upper bound. This is a very elegant little characterization of the least upper bound that is very useful in applying in using this notion. So where do we go with all this? I just wanted to use this in order to show you how the completeness axiom implies the completeness of the real numbers. So the idea is pretty simple. We start with a Cauchy sequence. And we realize that because of the completeness axiom, every increasing or decreasing sequence always converges as long as it's bounded. So in particular, if you take a sequence, let's say B1 less than or equal to B2, less than or equal to B3, and so on, which is bounded above, then it converges to the least upper bound of the set of its terms. And the same is true for decreasing sequences that are bounded below. In fact, if you multiply by -1, any bounded above increasing sequence becomes a bounded below decreasing sequence and vice versa. So technically, we don't even need to do much. So if we have a Cauchy sequence, there is a beautiful little argument, which sometimes we call the rising sun lemma. We should actually show this at some point, that says that every sequence has a monotonic subsequence, so either an increasing or decreasing sequence. So one starts with a Cauchy sequence, produces a monotonic, shows that it's bounded, then produces a monotonic subsequence, which of course it's also bounded, and by the completeness axiom of the real numbers, that has to converge. So we find a convergent subsequence. So let's explain it once more. Every Cauchy sequence has a convergent subsequence for the following reason. Because every sequence has a monotonic subsequence, every Cauchy sequence is bounded, hence the monotonic subsequence that we can choose is going to be bounded, and by the completeness of real numbers, every monotonic sequence that is bounded converges. So every Cauchy sequence has a convergent subsequence, and exactly because by definition a Cauchy sequence has the property that its terms come very, very close to each other, they also come very, very close to the terms of the subsequence that eventually pulls everything to the limit of the subsequence. So that's a very intuitive way to understand why a Cauchy sequence converges. And maybe for those of us who are not familiar with the notion of subsequence, let me just say that if we have a sequence, then what we mean by a subsequence is the choice of infinitely many of the terms of the sequence. What we sometimes do is we rename them, so we call, let's say, A2, we call it AN sub 1, AN sub 2, AN sub 3. So here N1 is 2, N2 is 3, N3 is 6, and so on. This is an arbitrary choice, of course, but what it shows you is that if you have a sequence and you want to consider a subsequence, all you need to do is choose infinitely many indices, so a sequence, a strictly increasing sequence of natural numbers that point to the terms of the sequence that we choose. So a lot to digest here, but and it might be useful to actually pause the video and go back and write some of these things down. But it's a good way to start appreciating what it means, how the axiom of completeness for real numbers establishes the fact that Cauchy sequences have to converge. And in the theory of Banach spaces, that's the thing that comes up over and over and over. In other words, the completeness of the real numbers is used in order to establish the completeness of different normed linear spaces. And that's all. Thanks for watching.